Alrighty, the last and potentially most challenging application of the ideal gas law is when we start to involve density. Okay, density, if you remember way back to the beginning of the year, is mass over volume. In gases, we are going to use the units of grams per liter. Okay, so if we take a look at this problem, it says, what is the density, that's what we're looking for, of NH3, that's ammonia gas, at 800 torr and 25 degrees Celsius. It doesn't seem like we get a lot of information, but in fact we do. We get a pressure of 800 torr. Okay, we don't get a volume. We don't get an amount. We do have the ideal gas law constant, 0.0821 liter atmospheres per mole Kelvin. And we get a temperature of 25 Celsius, which we all know by now is going to be equal to 298 Kelvin. Okay, the other thing that they give you is the identity of the gas. Okay, so if it's NH3, you know that it is 1 nitrogen and 3 hydrogens. You would or could look on the periodic table. 1 nitrogen weighs 14.01 grams, and you have 3 hydrogens, each at 1.008 grams per mole. So that gives us a grand total of 17.03 grams per mole for its molar mass. So you're thinking, well, how can I solve something with two unknowns? Well, if we use the ideal gas law to our advantage, we can manipulate any part of this equation so that we can get all of the unknowns on the same side. We are looking at volume and we are looking at our amount, our moles. So we can either move P over to here or R over to here and get everything, R and T over to there, and get everything to be the same. So let's see if we can work smarter, not harder. All right, if we have a molar mass, which is in the units of grams per mole, and I would like to get into grams per liter, what would I need as a conversion factor, dimensional analysis wise, to cancel out moles in the denominator and put liters there instead? I would need liters on the bottom and I would need moles on the top. So if I can get moles, or N, and I can get volume, or liters, on the bottom, if I can get N over V, I can just use it as a dimensional analysis problem. Okay, I can do that. So if I want N on top, I want to divide both sides by V, so my V will cancel out. And then I will get rid of R and T by dividing both sides by R and T. Okay, so this side on the right-hand side is going to be N over V, and my left-hand side is going to be P over RT. So I am going to solve for this ratio, and that's what I would plug in down here when I multiply by 7.03 grams per mole. So let's do exactly that. Okay, let's plug in. So when I plug in, I'm going to write it down here so that we can see it a little bit better. N over V equals P over RT. Our pressure is 800 torr. Hold up, we got to make sure we're in the right units because we have our gas law constant of liter atmospheres per mole Kelvin. So this is times 1 atmosphere over 760 torr, which is going to give us an atmospheric pressure of 1.05 atmospheres. So I plug that in. And then I'm going to put my 0.0821 liter atmospheres per mole Kelvin in the denominator times my temperature. And my temperature is 298 Kelvin. So you're like, how are all these units canceling out? I promise you they do. Atmospheres and atmospheres cancel out. Kelvin and Kelvin cancel out. So I'm left with 1 over, let's see, liters over moles. So I need the inverse of liters over moles, which turns into moles over liters. Hey, that's what I want right here. Okay, so put this in the calculator. 1.05 divided by, sorry about that, divided by 0.0821 divided by 298 equals, and I get a value of 0.0429. That has 3 sig figs, everything else has 3 sig figs. So let's make this magic happen. We're going to take our molar mass of 17.03 grams per mole. I'm going to multiply by 0.0429 moles per liter. And I'm going to watch my moles and moles cancel out and be left with a density in grams per liter. So all of this is to figure out the density. When I put this in the calculator, 17.03 times 0.0429, that gives me a density of 0.73, which, if you think about it, gases should be quite less dense than air and water. So you're going to see that it would float in water, which is good. So this is the density of NH3. Again, if you can't understand any of my handwriting in our notes, you'll see that that is all laid out for you. Okay, so we have 800 torr, which is 1.05 atmospheres. We don't know V or N, but we do know the gas law constant and the temperature. The ultimate unknown is mass over volume, our density, and we use the units of grams per liter. So the two unknowns in the PV equals nRT equation, the ideal gas law equation, are going to be V and N. We want to have them on the same side of the equation so we can calculate and change the molar mass from 17.03 grams per mole into grams per liter. So the way that we do that is by solving for moles over liter. That way, moles and moles cancel out. Well, moles over liter means that we need N over V in our ideal gas law equation. So it's N over V equals P over RT. Okay, and we substitute and plug into there. So N over V equals P over RT. We plug in 1.05, 0.0821, and 298. It will cancel out atmospheres and atmospheres, Kelvin and Kelvin, and I get 1 over liters per mole. So the inverse of liters per mole is moles per liter. So yay, algebra is working for us here. And we get that 0.429 moles per liter. And then simply take the molar mass that we calculated for NH3. We get this from the periodic table. Multiply by our answer we calculated using the ideal gas law. And we see that moles and moles will cancel out, leaving grams per liter, which is a perfectly acceptable unit for density. We love density. So you will see lots more of these in these level 2 problems.